Okay, so the purpose now is to extol the wonderful virtues of equalizers. Um, we've already seen that products are very, very useful in category theory. And obviously, limits are very useful, but limits are a very general kind of concept, or seemingly so. But what I want to try and demonstrate today is that basically if you have products and you have equalizers for any stuff you want to do, let's say you have products for every pair of objects, so that means you can iteratively build up products for many objects. And let's say you have equalizers for every pair of arrows, every pair of parallel arrows, they'll be our assumptions. Well, in that case, you actually can get any limits you want. You can construct limits made out of products and equalizers. Now, just to say something else that's cool about if you have products and equalizers is that you can get pullbacks. I mean, if you think about in sets, for example, the pullback of a when you have like this kind of situation, I'll just draw it somewhere. So it's a general pullback. Well, the pullback of this F and G, at least in set, you can think of it as the set of all pairs of an element from A and an element from C, such that F on the first element equals G on the second element. And if you think about it, that's actually a subset of the product of A and C. It's actually the subset of the product of A and C that if you do the first projection on it in an F and the second projection on it in a G, you get the same result. And in fact, I mean, if you think about it, that means you can basically think about it as an equalizer involving the product of A and C, and that precisely holds in general category theory. So if you have products and equalizers, you can talk about pullbacks, but there's much more to an equalizer than that, and we're going to see how we can represent a general cone. I mean, a general limit. Okay, so the setting is that we have a limit. So I'll just quickly go through the definition of a limit again. So we have this constant functor. So we've picked an object t of c, and we have this constant functor delta t, which sends every object of I to t and sends every arrow of I to I dt. And a cone is just a natural transformation from delta t to A. What's A? This is capital A. A is the functor that we want to take a limit of. A is just a generic functor from this index category I to C. Okay, so a cone is just a natural transformation from the constant functor to this functor of interest. And a limit is a limiting cone. So it's a cone. So we're on about the limit of a functor array from I to C. It's a cone delta L phi. It's a natural transformation from the L value constant functor to A, and we call it phi. That's our limit. We can also sort of include the apex L as part of the notion of the limit, but in this notation, it's kind of clear that we need to know what L is as well. It has to be such that for any cone phi, there's got to exist a unique, for any cone psi from delta t to A, there's got to exist a unique u that's going to be an arrow from the apex of psi to the apex of our actual limit phi, which has got to be such that phi after u equals psi for every object I in our index category. So this is the picture. The red thing is our limit cone. The blue thing is our kind of candidate cone with the psi, and there has been this unique intermediary arrow which makes for triangles involving that green arrow commutes. Okay. Now we want to construct a limit using just products and equalizers. So what we're going to do, this is going to be the product, pi is going to be the product of it's going to be the product of all of these objects in our diagram, you know, A1, A2, A3. I'm going to sometimes think of this index category as objects labeled by numbers. It's just going to be easier for notation. So these I's and J's, maybe I'll sometimes, you know, write them as 1 and 2 and so on. But that's just a matter of labeling. Now, we've got PJ, which is taking the J component. It's a projection from this product. And here's a bit of notation which I don't use very much actually, but for a arrow F from J to K in this index category, with a subscript F equal AK. So another way we could write this is A of target of F, because K is the target of this arrow F from the index category. Okay. So the other thing we consider is that we take a product over all the arrows in the index category I of A subscript F. So another way we could write this is we product over all the arrows of A of target of F. I think that's better notation actually. It's more clear. Anyway, and then we have projections Q of F dash. So how are we to visualize this? Well, we have all these arrows in our diagram, and for every arrow we just take the object as its target and we product them all together, and that's what this is. Okay. Now here's the mind stretching bit. We have an arrow R from this product of objects to this product of targets of arrows in the diagram. Well, I should say we visualize this here. Really, it's the for every, because we could be mapping some of these on top of each other with our functors. So it's really the product over the arrows in the index category of the target of where they get lifted, if that makes sense. Anyway, this is the mind stretching bit. We have this arrow R from this product of objects in the diagram to this product of targets of arrows in the diagram, and it's supposed to be such that for every arrow F dash from J to K in our index category, this diagram has to commute. So we have to have that Q of F dash after R equals P of K. Remember, Q of F dash is the projection from this product of arrows, product of targets of arrows here. So how are we to visualize this? Well, intuitively, like say this H was a 1 here and we're working in the category of sets. So V here would just be a, yeah, when I'm saying working in the category of sets, I mean just temporarily assume that C is the category of sets. So this V here is just picking out a tuple. So we're going to have, the first entry from A1, the second entry from A2. It's just basically picking out a tuple with one element from each of these sets. And so PK just takes the kth one. So we can think of an entry like that as X1, X2, X3, X and so on. And then, so PK would just be XK, the kind of kth member of this tuple. And that ought to be the same as what we get if we take this tuple and we do R on it. So then we get a tuple of targets of arrows, and then we do Q of F dash on it. So we take the F dash entry. So basically the result, if this thing is RV, if V is this tuple, RV is this tuple of targets of arrows where the FMth member of this tuple, as in the element of F, the sort of entry of RV associated with arrow FM, is equal to X of the target of FM. So basically, all we're doing is, like, we have this load of arrows here, and with V we have a sort of assignment of a value into each AI, so each kind of object in the diagram, if you like, and then all we're doing is associating each value, so associating each arrow F with the entry which is assigned to the target of that arrow by V. Okay, so it's just sort of like a translation. I mean, with V, we label all the objects, and then RV is going to sort of label every arrow with the thing that its target got labeled with V. That's basically it. Now, this can all be made much more precise without having to hand wave and think about the category of sets. If we think about generalized elements, so there's a very nice notation, very nice idea, is that a sort of H element, or sometimes called a H figure of A, is just an arrow from H to A. So we write X is in with a subscript H and then A to just denote that X is an arrow from H to A. And we could call this a sort of generalized element or a H element. We could say X is a H element of A. So that's cool because it turns out that when we have a product, well, there's two things. One is that when we have a product, H element of that product directly corresponds to like a H element for each object involved in that product. So we can just think of, just like we do in sets, we can just think of just as we do in set with arrows for terminal objects. In general, we can just think of the H elements of the product as like a tuple of H elements from each of the things that we're producting together. And then secondly, we have this very nice result that in general, an arrow F is going to be equal to an arrow G when f of x is equal to g of x for every generalized element x in A, or where f and g are both arrows coming out of A. So basically, this is just saying that if your arrow composes of any other arrow, if you've got two arrows and each have a property that if you compose them with anything, you always get the same result with using either one, them two arrows are the same. So that's very useful because it basically allows us to formalize and really gives teeth to this idea of using tuples. Anyway, back to trying to understand what R is, which I think is probably the hardest part of this. Basically, if we have a generalized element, then a sort of H element or H figure of this product of objects, we can just write that like officially now as a tuple x1, x2, blah, 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 where x1 is a H element of A1 and x2 is a H element of A2 and so on. And then, when we do pk on V, we're just selecting the kth entry from such a tuple. So pk of V is just xk. And we want that to be equal to the thing we get when we go the other way around the diagram. So we want xk then to be equal to, so when we do R of V, that's going to give us a tuple, like again, because it's a H element, we can think of it as a tuple of entries, from A of the target of the first arrow, then A of the target of the second arrow, then so we can write it as yf1, yf2, blah blah blah, where yfm is a H element of A of target fm, and then this results that we're saying that if we then do the Q of F, the projection on that, that's just going to actually select the Y. Say if we do the Q of Fm for projection, that's just going to select the YFM. So basically what we're just saying is that the sort of YFM for entry in this tuple RV, so that'd be Y of Fm, is just going to equal X of target FM. So all this is really doing, this R, we'd see it's uniquely defined now because we have this kind of relationship holding for any H figure V, for any H. So by that result I just said, this uniquely defines it. And basically all it does is it takes an assignment of H figures to these different AIs, and then they're sort of like objects, and then it looks at this tuple of arrows, and it assigns each arrow to this corresponding kind of place. So I mean, basically all it's doing is making sure that the targets of these arrows are acting like the things that they should do in the way that this V assigns stuff, but it's doing this in these kind of with these kind of bundled products. Okay. So the next thing to define is this S here, and this is similar. Again, it's an arrow from the product of the AIs to the product of over the arrows of the index category of A of the target of the arrows. But it's a bit different this time. because now we have this, instead of having that triangle commuting for every arrow f dash from j to k, now we have this square commuting. So we basically want that the thing that the arrows, like we take in a tuple, well, okay, I think I've got a better picture here, yeah. So we take in this tuple of h figures, so an assignment of a h figure xi to each ai, and then if we go this bottom way around the square, we're just taking the xj here and actually operating on it with the lifted version of this arrow. And then if we're going the top way around the square, what we're doing is we're changing this into a tuple of arrows, and then we're taking the f dash component of the arrow. So if we do the math, we get that the this h element here of this product of targets of arrows, we can write it as SV, and as we say, it's a tuple y f1, y f2, and so on. And basically we have that y of f of m, well, we can write that as q of f of m sv, and then using the commuting square, we get that's a of f of m pjv, so it's a of f of m xj. So basically, what this is doing is it takes an arrow. I mean, all this is doing up here really is it takes an arrow, and then it figures out what its target's assigned under v. But what this does down here is it takes an arrow, and it looks at the source of that arrow, and it lifts the arrow under A and applies that mapping, so actually in the diagram rather than the index category, and that's what it's corresponding, that's what it figures out how to do with an arrow. Okay, so we get that SV is this tuple where y of fm is a of f of m x of j, where x of j is the kind of h figure assigned to the source of this arrow, the source j, under this kind of bundled together h figure v of the product of the AIs. So that's just a little bit about trying to understand what's going on. It's maybe overdone it a bit because the proof is a bit more kind of grounded, but now here's the main claim. The main claim is that, consider the case where we, like, an equalizer of these parallel arrows R and S. So an equalizer with an object capital L and the sort of monic part of the equalizer, this little L here. It's going to be an equalizer of R and S if and only if we have that this is a limit here, this phi from delta L to A, where the ith component of phi is pi after L. So it's fun to do this intuitively, because we can just ask simply, what's it mean to have, I mean, very intuitively, like in set or whatever, an equalizer just figures out the elements of this thing, but doing this function on them gives the same result as this one, takes that subset, and we can just think of it as an inclusion function. Okay, so let's take that kind of view. So what are all the elements of here such that so V, let's take the H elements, V such that R of V equals S of V. Well, we want the R of V of F of M, so that's X of the target of F of M, where X is this H figure of the product here. We want that to equal S of V of F of M, which is A of F of M of X of the source of F of M. So what this is basically saying is that these, I mean, this is looking exactly the same because, I mean, this is looking exactly the same as the kind of definition we get when we do the normal kind of limit in set. I mean, a limit in set is basically just Cartesian product of all of the sets involved, and take all those tuples and then select a subset of them which have the property that, you know, whenever you have a kind of lifted arrow in the diagram, say from AI to A, sorry, say from AJ to AK, an arrow F, whenever you have an arrow F from J to K in the index category, you have a lifted arrow A of F from A of J to A of K, and if you do it on like X J, where you have this tuple of X's, then you should get XK. So it's basically just that exact same kind of thing. So that's the basic kind of intuition. Now, as an interesting thing here is that basically we can sort of define it as a subset, and that reminded me of something, which is another very interesting characterization of the equalizer. I mean, we're seeing here that equalizers are extremely important, but I'll get into that later. Let's get into the proof of this result, or at least as much of it as I can do at the moment. So suppose we have a cone, psi from delta t to a. So its ith component is going to go from t to a of I. So we have all these components. So we can think of those as a tuple, and we can make a product. So we can have this intermediary arrow from t to the product of these AIs. And just pi being the projection under this product, we have pi of h is psi I. Okay, that's just a definition of a product. Now, what we have, another result which is kind of interesting, is that in general we have RH equals SH if and only if Q of F dash of RH is Q of F dash of SH for every arrow F dash in our index category. So to see this, we just draw out this diagram, and then we see that like Q of F dash of, say, S of H is just going to be, well, we know that S of H is just going to be a arrow from T into this product of targets of arrows here. So it's going to be a tuple. So both of these things, RH and SH, are just tuples, and they're only going to be equal when each of their components is equal. And when each of their components are going to be equal, they will be equal. So that's why we get this result this way. Okay. Now, so we have RH equals SH is equivalent to this condition here. Now, what does this condition mean? Well, I think I meant to put, that ought to be a psi j there. Yes. So basically, this is our condition for psi being a cone, because we want that psi of k equals a of f dash after h of psi of j for every f dash from j to k. How can we see it? Well, for f from j to k, we have q of f dash rh equals pk of h equals psi k, and that just comes from our first diagram involving the definition of r. And then q of f dash sh equals a of f dash bjh equals a of f dash psi j. So this equality here again just comes from a definition of s. So remember these diagrams here, defining s and defining r. Okay. So yeah, so we have these results. And I mean, we've defined this L thing here as the equalizer of R and S. So the big kind of punchline then is that RH is equal to SH is equivalent to saying that H factors uniquely through L. Well, that just comes from the definition of an equalizer. Because, you know, since we know that this is an equalizer, we know that if we have this candidate H here, then there has to exist this unique R such that L after R equals H. And then that's equivalent to saying that this cone T comma psi factors uniquely through the cone L pi after L, because we have this unique R here, and if we look at the condition that we want for, you know, like one cone, our limit cone to be better than this other cone, it's that there exists this unique R such that pi after L after R equals psi I. Well, pi after L after R is by this picture is pi after h, which is psi I. So this is pretty much the idea. Although admittedly I do have to think more clearly about some of the details here. Anyway, the other thing I was talking about was these equalizers, and then there's a very nice result about that, which is here. So it's a bit simpler. So the key definition is if we have an arrow I from A to C and an arrow J from B to C, then we say I is in J if and only if there exists a K such that JK equals I. Okay. Now here's a nice theorem characterizing equalizers. A monic E is an equalizer of parallel arrows F and G from A to B if and only if for any x, we have that x is in E in the previous sense, if and only if f of x equals g of x. So in terms of generalized elements, what this is really saying is we can think of, I mean, E is a sub-object, so we can think of it almost like the collection of elements which are equal. I mean, it's really pleasant, it's really simple, like it is in sets. Anyway, what's the proof? Well, suppose we have number one, so we want to show number two. So suppose f of x equals g of x. Well, from the definition of an equalizer then, there's going to exist a unique h such that e of h equals x, and that means that x is in E. Now we've shown that the right implies the left. Now we're going to show the left implies the right. So suppose we have x in E, then there's going to exist a h such that EH equals x. That's just the definition of x equals E. And now we have that because E is an equalizer, we have that f of E equals g of E, and so f of EH is equal to g of EH, so that's f of x equals g of x. So that's what we wanted. So we've proved that 1 implies 2. Now we want to show that 2 implies 1. So assume 2. So note that E is in E, so we have to have that f of E equals g of E. So we've got that it does actually equalize f and g, but is it an equalizer? Well, let's suppose that there's another there's another x such that f of x equals g of x. Well, then this result gives us that x is in E, so that means that there's got to exist this h such that x is equal to EH, but know that E is monic. Okay, so since E is monic, it must be a unique h, because if we have EH equals x and EH dash equals x, then h equals h dash because E is monic. So this E, which sort of is this intermediary, is a unique intermediary. So we have that indeed E is an equalizer. So we've shown that 2 implies 1.